Thank you for watching Knowledge Academy.
So first thing first, what is a divergence theorem? And the basic idea of divergence theorem is that we have two theorems left. One is Stokes theorem and one is divergence theorem. I'm going to talk about today divergence theorem and then we move into the Stokes theorem. And divergence theorem is that divergence theorem calculate or evaluate the flux going in and out of the solid. Solid body through its boundaries, right? For example, you have a room, you know, you have a room and what's happened, this room have 8 sided, and let's suppose the cold weather is cold weather, and you are living inside the house, that's your house. And what's happened, you just having a cold, so you try to use a little heat generator. So you putting an electric wire here to heat this heat, basically go to the heating the room or house so you can live there comfortably, and that is called heat. But some of the heat come out of these valves and start passing here, you know and that is Q, which is a heat flux, right? It could be heat flux, this could be magnetic flux, could be any quantity. Flux means any quantity coming out of the system per unit area, right? Per unit area is a flux, means larger the area, more the flux is. And that is how we calculate the divergence theorem. In regard of Stokes theorem is different. Stokes theorem is, if you have a room, right, how much heat coming out of this wall, or maybe you have just have a window, how much heat coming out of this window, that is a Stokes theorem. And it's mostly on certain direction. So this heat coming out of this, that is a Stokes theorem, right? And this is a Q, heat flux, right? So bottom line is that is another important essential thing is, when you talk about the Stokes theorem, right, these boundaries are very important. And when I say very important, means if you go this way, then you talk about green theorem, right? Remember, if you remember green theorem, we talk about it. In green theorem, you have like a surface, and anti-clockwise is considered as a positive orientation or positive direction. It means if you go into the right direction, arrows is Q coming out. If you go to the other way, like you move the direction like this way, it's gonna be, it means is heat is actually going into the system. For example, in summer, what's happening in summer, summer is outside is hot, your room is, or your home, you want to keep it cool, so you turn on the air conditioner, and it keep the temperature below in the house. And what's happened, the heat from the outside is going into the system. That is why this red color orientation is very important in Stokes theorem. We're going to talk about that when we go to the Stokes theorem, but that's the major difference between the two. Okay, let's talk about some mathematical for divergence theorem, mathematical implication of divergence theorem. Today our topic is divergence theorem, by the way, and the flux of the vector field. You know, the flux of the vector field F through a closed surface S is equal to the integral of the divergence divergence of F over the entire enclosed volume. Okay, and how can I write this? I says, well, if you have a if you want to calculate the flux of n in the direction of ds, so really what does that mean? It means if you have a system, let's suppose you have like a hard potato. If hard potato is have temperature of 70°C, right, and your room temperature, you bring a hard potato out of the stove and put it in a room, and your room temperature may be 22°C. I don't know what is the temperature you keep it in the room, but that is the thing. So what's happened, this heat is going to come out this in all direction. The potato want to be cooled down and room want to be take this heat because potato want to be normalized. That's why after a certain time the potato temperature is same temperature as the room temperature, right? And definitely you need some medium, so that's the air is gonna go and then pass over the potato. So if you turn on the fan, it accelerates the process, right? But even though you don't accelerate the fan, don't turn on the fan, you still have the air in the room, and this is my field called F. So what I'm going to do, I'm going to take this F and this F, my total field, and I'm going to be calculating a little piece of potato. I'm going to cut it out, this piece, and I want to know that how much heat going out of this one, so I'm going to call them ds, and then I'm going to be using this little area of the field, how much field coming out of this, I'm going to say make it F, and then little area of this red color patch is normal to the, so this is a red color piece, red color patch, right? This is ds, the area of this is normal n, and that is my vector field, and that is how I write. And this is s is entire surface, like this is entire surface. And definitely you can take another red color piece. So what exactly doing, we take this potato and then split into pieces, right? And every piece we can apply the same thing. So this is empty. Divergence theorem says, I'm going to say right here, flux, what is this whole thing? It's going to say flux through S. S is the whole surface area, and I'm going to call this S. Okay. Now, divergence theorem says you can calculate this in a much easier way, and the easier way is this. You take the gradient of F. Actually, we know what is a gradient, we know what is a field, we know what is a dv. Dv means 3 operator, dx, dy, dz. If it's a circular, it's a spherical, it's not a potato, it's a sphere, then you can apply spherical coordinate. If it's a cylinder, you apply cylindrical coordinate. If it's just a shape, rectangular shape or a square shape, you apply coordinates, just like x, y, z, rectangular coordinates. Okay, you can apply this one, and let's take a look on how does it work. But before we do anything, I just want to make sure that we always remember this is a dot product between the two. And if I write like this, it means I'm writing this gradient, which is I'm writing like this. And this guy is fx, fy, fz, I, j, k. If you want to write like this is pretty much what does that mean. Okay. You can also call this is divergence, right? This is how you calculate. This is also you can call also says divergence of f. So I can also write this is called divergence. And that is why we call this is divergence theorem, right? We already calculated divergence earlier. This is today we call about theorem, and that is what the whole concept came from, divergence theorem. Okay, let's take a look at an example. Flux. When I say flux word, flux probably you guys learning about in physics mostly. Flux means a quantity emission or absorption. Emission or absorption per unit area. Right? Just like you have a light bulb, you know, and then light coming out. I say, wow, it's a very bright light, right? But if I want to know that, you know, if I have a two light bulb, I have a small light bulb, and I want to compare the two, and I want to compare, I said, how can I compare it? What I'm going to do, I'm going to take a little piece from here, and then see how much light coming out of this and how much light coming out of this. And I'm going to maybe I can call L over A and L over A. Or you can call E over A. Light is energy, so you can call E over A. So this is basically the light flux. Same thing with magnetic flux, same thing with whatever flux you want to be calculating. But we are not worrying about what is a flux is. I just give you a brief introduction about what is a flux. Flux of a function, and function is a field given xy square, xy square, then xy square, then xy square, some field out of a unit cube. Okay. And maybe unit cube means every side is 1, 1, 1. This unit cube, and this is 1, this is 1, and this is 1. Every side is 1. So what I'm going to do, I'm going to go here. I'm going to say is I think it's not. I'm just write this thing here. Let's change the field x, y, c, x, y, c, x, y, c. Okay. So my first field is the partial derivative of the first fx with respect to x is yz plus partial derivative of this with respect to y is going to be xz plus the partial derivative of the last term with respect to z is going to be xy. Okay, and I'm going to say is as per divergence theorem, I'm going to be writing divergence theorem real quick here so we remind ourselves what is that. F and ds both are vector. ds equals to triple integral of v partial gradient of f and then d B. This is our divergence theorem. I'm going to apply same thing here. I'm going to be writing 1, 2, F and ds equals to 1, 2, 3, and then my function, which is this dot this dv. So I'm going to be changing accordingly, and I'm going to write it like this: y z plus x z plus x y. This is what I just calculated. And then dx dy dz, volume can be converted into these three. And then 0 to 1, 0 to 1, 0 to 1. How? Because the unit from one, this point is 0, 0, 0, and if you go here, this is x, this is 1. If you go from here, this is 1, and if you go up in z, it's gonna be 1. So I substitute this, and I take the first partial derivative, sorry, first integral of 0 to 1. So this is gonna be with respect to dx, so it's gonna be yz plus z over 2. I'm also substituting the value, so z over 2, and there should be x here, but I substitute the value of 1. I substitute the value of 1, and plus y over 2, and then substitute the value of 1. And it's going to be dy dz. Same thing, I'm going to take the drag integral. It's fairly simple integral just to demonstrate this phenomena. So z over 2, z over 2, 1 over 4, z over 2 plus z over 2 plus 1 over 4 dz. Then I take the last integral, is going to be 1 over 4 plus 1 over 4 plus 1 over 4, and everything equals to 3 over 4. Okay, and that is my flux going through this surface out of that. But think about it, if you just make it double, like let's suppose the cube is getting double in size, then everything should be changing. Like if you make double cube, so this is 2, 2, 2. So if you change everything changing over there, you can calculate it again. It should be double than this. Should be exactly, you can take this and multiply by 2. And the answer would be 3 over 2. Right? And if you, this is a mathematical proof. If you solve it, everything in with the different limit, it should be coming 3 over 2. Okay, so I'm just giving you this as a checking point to check this. Now take a look on some other problems. Take this problem a little bit complicated this time than the previous one. Previous one was less like a demo. Use the divergence theorem. To evaluate this. By the way, in green theorem I just wrote like this integral and have a little circle. If you no circle, you still have this s dot ds. So make sure you catch up this one. It's already mentioned and use the divergence theorem. But if you don't mention the divergence theorem, if you have these kind of things are written, you know that this is something belongs to divergence theorem. And then f is a field given is sine pi x I plus x y cube z y x y cube j plus z square, this is going to be, it's going to be z actually, and this is going to be z square plus 4xk is the surface of the box with -1, and then y is also going from 0 to 1, and x going from z going from 1 to 4. Okay, and I'm going to say is note that all of the sides of the box are including the s. And what does that mean? It means note that all the 6 sides of the box including on s. It means I have a box like this, is going from 0 -1 to 2, right, and is going from 0 to 1, and then going from 1 to 4. So really this box is located somewhere, it's not on this side, it's on the other side. So I'm going to just draw the box. It's going to be look like this. But this box not starting from, this is z by the way, it's not starting from 0, it's going to be starting from 1 to 4. So this is 4, this is 1, so it's going to go a little bit further that I'm getting 0. From here, maybe not this yet, maybe this. And the back side is coming, this side is going there, this side is going there, but the back side is coming like this. Okay, I'm not interested in really the below box. I'm interested in the goal in the upper box. And upper box we have, this is 0 to 1. So this one is 0, this is 1. So it means this is also 1. This is 0 in x. This is y. In x is starting from, that is my y side, that is my z side, that is my y side, and that is my x side. X starting from here is -1. It's going on the back side, and this side is basically 2, right? It's giving it that. So this side is giving this 2, and this side is -1. Anyway, I'm only interested to find the flux on this side, on the top box. I'm not interested in the bottom box, because bottom box is where is not the bottom box, is just a empty cube. I'm interested on the top cube, which is my coordinates are given. Okay, so I'm going to be writing the divergence theorem. Is going to be like this. The divergence f, I can write this time a little bit different. We know divergence f means delta or gradient dot f. I wrote here, and then I write my x limit, y limit, z limit, x going from -1 to 2, and this one is 0 to 1, and this one is 1 to 4. Okay, then I'm going to calculate in the divergence of, this one is also written like this. So this problem is going to be covered bunch of different things in a very best way. And then take the second partial derivative with respect to y for zy cube. And this one is done. Then I take with respect to dz, and it's going to be x cube by x squared plus 4x. X squared plus 4x, z squared plus 4x. If I take the partial derivative with respect to all of those, it's going to be pi cos pi x. Here is a y is going to be 3xy, 3xy squared, sorry, plus 2x. Right, this is x cube. It's going to be supposed to be just z, 2z. Okay, we take the partial derivative of all of those, and then I'm going to be substituting into the function. So remember, left side is a 1 I wrote, right side is a 1 I solve. That's usually I keep repeating that word because it's important to reminding ourselves which side I'm solving. By the way, two vectors. I don't use the n here, so I have to put the little tag on this s or ds, and I'm going to be just substituting the three limits. So it's going to be pi cos, I'm just writing this guy because I already calculated this divergence, three xy let's see, maybe the second term, let's see, yeah, I messed up here. Okay. And I'm going to be just writing into that directly since I already know all these value, pi x plus 3 zy squared plus 2x dx 2z dx 2z dx dy dz. Okay, so I have a dy first, dx first. So zx go from 0 to 4, no, 1 to 4, not 0 to 4. Dx go from 1 to 4, y go from 0 to 1, and z go from minus 1 to 2. Okay, let's take another. So I'm going to be just leaving the first integral and second integral as is, and do the so let's do this one. It's going to be x, maybe 3 pi cos pi x plus 40 plus pi z. This is that I'm not going to say directly repeat pi z cos x going to be 3 by 2 z square y square plus z square. Okay, going to be 1 to 4 dy dz. Let's substitute the value. Probably we have to go to other slide. So 0 to minus 1 to 2, and then 0 to 1, and let's substitute the limit. So pi cos whatever this is pi, cos pi x plus 45 over 2 y squared plus just 15 d by d. Okay, I'm going to write this thing into a second slide and then continue. From the previous slide we wrote like this: minus 1 to 2, 0 to 1, 3 pi cos pi x plus 45 over 2 pi squared plus 15 dy dx. One to 2, 3 y pi cos pi x plus 15 over 2 y cube plus 15y 0 to 1 dx. Okay, I take the second integral, and now I'm going to be about to a little bit simplify to put the limit before I take the third integral. So it's going to be, sorry, to my integrals today, and 3 pi y cos pi x plus 45 over 2, I just putting the value of 1, and then dx. And now I'm about to take the last integral, so it's going to be 3 sine pi x plus 45 over 2x 2 and minus 1. Okay. If I take this value, substitute into the problem, is going to be look like 1, 3, 5 divided by 2. Everything will be gone. All you have to do is take the sign, 2 pi, first 2 pi, and then sign minus pi, and take the values, actual values, and then solve them. If you give the answer in decimal is also fine, but usually flux is a little bit tricky because you don't want to be dealing with the flux. You don't want to be dealing with the flux on a decimal points because some of the points may be missing. Okay, let's look another problem. Here in the divergence theorem, the only problem is again the shape of the surface, because that's actually causing challenges if you want to be doing some limits. Okay, let's do another problem, have a different kind of shape. Use the divergence theorem. To evaluate, and S, F, ds both should have the vector because I don't have an n here, where F is giving something look like this: x y I minus half y squared j plus c k. Okay, and the surface consists of the three surfaces z equals to 4 minus 3x squared minus 3y squared, and the other side of giving is, this is one side, and z is going from 1 to 4, and the last one and on the top is equals to x squared plus y squared equals to 1, and the other side is giving 0 to z1 on the sides, and z equals to on the bottom. Okay, so we have a bunch of surfaces are giving just like, so really what is that? Z equals to 0, so 3 words here. Consider of the surfaces, so this is the first, and this on the top, so this is up to much this, and this one is on the side, right? So really the shape is giving it like this. If I draw the shape, then it makes sense. It's going to go from 1, this side is going to go from, like, this is the bottom pretty much, so it's going to give it like, and it's going to go up, and from here it's going to be basically like a dome, right? And this is a shape, so we need to calculate, and this one is y axis, this is one is x axis, and this one is z axis. Okay, so really what I'm going to do when I draw the line, I'm going to take this and then draw the line from here to there. Is cutting here, is cutting on the bottom surface, right? So I'm going to write in 3 values, or 3. So my z, my r, my theta, right? So really what I'm going to do, I'm going to take this, make it like a cylindrical coordinate, like this is a cylinder, right? It's a cylinder, and the other one on the top we can take care of the z. So I'm going to be writing 3. Z is going from where to where? 0, top surface is this, like this. So I'm going to be writing 4 minus 3x squared minus 3y squared. The radius of this is going to go from 0 to, you know, this is a circle is giving with 1, so I can say from here, if I make a r like this, it's going to cut r equals to 1, it's given here. So I'm going to say is r going to go from 1 to 0, and theta is very simple, it's a complete round, so it's going to go to 0 to 2 pi. Okay, now take a look on this. So I'm going to say is 4 minus 3x squared minus 3y squared. I'm going to say is 4 minus 3x squared plus y squared, and I can say is 4 minus 3r squared. So I can get rid of this guy and write him in the form of r. So 4 minus 3r with the square. Alrighty, now it's pretty much very simple problem for us. It's all about this. Let's start solving. I'm going to take divergence of f, so it's going to be y minus y plus 1 equals to 1. If I take the divergence of this, it's going to be y minus y plus 1 equals 2. Everything will be cancelling out, so it'll be getting to 1. So I'm going to be writing according to divergence theorem, and right side I'm going to be solving, left side I'm just going to be writing, call V, and divergence dV, and this one can be written like this: 1 2 3 0 to pi, sorry 2 pi not pi, and 0 to 1, and 0 to 4 minus 3r square. Inside I have a 1 here. Usually we don't write 1, but this is the one is coming here, this one. And then dv, so dv changed to r dr d theta. If you remember, I'm going to say the same thing: r dr d theta. In this, sorry, this should be a dct, it's a volume. So I'm going to writing same thing, I'm going to go r dr dz d theta. I'm going to say accordingly. I think I messed up a little bit with these. So my first one will be r, so it's going to be dz. It's going to go to the dz. So the first limit is should be dz, because this is a dz limit or a z limit. The second limit is r, so dr, and the last limit is theta, so d theta. These are very important order. If we screwed up with these order, our answer will be completely wrong for no reason. We just make a small mistake. So I'm going to take the integral of this. It's going to be 4r minus 3r cubed dr d theta. I take the second integral, it's going to be 0 to pi left, 2 pi. And if I take with the dr, it's going to be 2r squared minus 3 over 4r, 4, 1 to 0, and d theta. If I take this integral, it's going to be 0 to 2 pi 5 over 4 d theta. If I take the last integral, it's going to be equal to 5 over 4 and then just pi. Right? It's cancelling out. But I forgot this to make it cancelling out. 2 pi cancelling out by 2 becomes 2 here. And that is pretty much our answer is. Yeah. Let's do another problem real quick. Let B be the solid let B be the solid region lying between the plane x equals to -1 and x equals to 1 and y equals to 0, and then y equals to 0 and then y equals to 2, and bounded below the plane zero and above the plane above the plane. Z plus y equals to 3. Let S be the surface of B find the flux of the vector. And the field is giving something look like this. I think I make parenthesis in the wrong location. Here, y square z plus cos pi y. This is I. Y z plus sine pi z is my j plus x minus y square is my k. Now first thing first, before I do anything, I'm going to be putting the values, and really what is giving, this time we don't want to be making the box, but it's saying that the surface area of x equals 2 is exactly the same location, like you have like a box, you have a box is given, and this is x value, this is a y, but the bottom one is your 0, and the top one is the top of the box is this guy. Sorry, the below is this one, and the other side is that side. So what I'm going to do, I'm not going to make the diagram, I'm going to solve it without the diagram this time. This is what our practice is, and I'm going to take this into the gradient of this. So this problem we're going to be solving without the diagram to make sure we don't rely on these diagrams all the time, because sometimes the diagrams are not given. And I'm basically nothing, just rewriting my given function in the partial derivative form, so I can take the partial derivative of this, and if I take the partial derivative, it's going to be just 2x z plus, this one is 0, this one is z. Yeah, other than that everything will be 0, because here no function of y, here no function of z, so everything will be 0. So 2x z plus z. Look like our job is much easier this time, hopefully. Let's see what's gonna happen. So first thing first, I'm going to be writing the green theorem of the divergence theorem, and it's going to be this. I'm going to be writing again our old way, right? And I'm going to be substituting the values 1, 2, 3. That's my b, you call it v if you want to. This is pretty much the same standard I used to write. And I'm going to write in here 2xc plus c d b. Writing my limits here, my x, y, z. So x go from 0, 1, minus 1 to 1. Y goes to 0 to 2. That is given in the problem right here, 0 to 2, 0 to minus 1 to 1. And then z goes to 0 and 3 minus y. So what you do, you take this guy and move the y on the other side, so it becomes c minus y. Okay. So I can write this integral in the form of 1, 2, 3, and then split all of them, dx, dy, dz. Okay, here So I'm going to be writing this, and then minus 1 to 1, 0 to 2, and then 0 to 3 minus 1. And now take the integral, is going to be half with minus and dx minus 1 to 1, from 0 to 2 dy, and then 3 minus y squared. Then I'm going to write one more time. Minus 1 to 1 dx 3 1. And what I did here, I really did the substitution. U equals to 3 and minus y, and then here du equals to minus dy. This is what I did. And then du, and then u squared. Okay. And if I take the right side integral, is going to be 1 dx. This integral will be 1 cube over 3 minus 3 cube over 3. And if I take the last integral for this one, it's going to be 26 over 3. Okay.
Thank you for watching Knowledge Academy. Please subscribe my channel.